this recording to my YouTube channel as always. So let's get started and talk about chemical reactions and equations. The last lecture, we spent a lot of time looking at stoichiometry. So that was relating numbers of moles to grams. And what else did we talk about? Molar masses, formula units, formula masses, and all those kinds of things. But tonight we're going to focus on chemical reactions and using a lot of the skills that we learned in the last lecture to help us understand chemical reactions even better than we could without that information. So it says here, chemical reactions and equations. And what else does it say? It says a process in which one or more substances or substance is changed into one or more new substances is called a chemical reaction. A chemical equation uses chemical symbols to show what happens during a chemical reaction. Now on the left-hand side, we put the reactants, and on the right-hand side, we put the products. Now it says here that there's three ways of representing the reaction of hydrogen and oxygen to form water. Now the way that I would describe it is this. I'd say, okay, well, I know that hydrogen is a diatomic element. Okay, when hydrogen exists by itself, it's H2. And I know that hydrogen is also, I know that it's a gas, right? I know that. Also, oxygen is one of the diatomic elements, and it should be a no-brainer that oxygen is also a gas. And when they combine, they form water, H2O, and water is a liquid, and that's what the L stands for. So G is for gas, L is for liquid, and you probably know this already, I'm just rehashing here. S is for solid, and AQ is for aqueous solution. Now remember, water is not AQ, water is not aqueous, water is pure, okay? It's a pure molecular compound, and so it's a liquid. Now this is not a balanced equation, okay? And why is this not a balanced equation? Because if you look on the left-hand side, I have two atoms of oxygen here, right? There's two atoms of oxygen attached together, but I only have one on this side. Now, how would I balance that out? There's a couple of ways that you could approach this, but one of the easiest ways would be, okay, if I multiply 2 by a half, right? If I take the number 2 and I multiply it by a half, what do I get? I get 1, right? So if I have 1/2 of O2, that means I'm going to have 1 oxygen. So that gives me 2 hydrogens plus 1 oxygen gives me H2O, which contains 2 hydrogens and 1 oxygen. Now, something that I've learned since moving to the United States is that generally we don't leave fractions in equations in chemistry. We usually multiply so that we can get rid of those fractions. And what do you have to multiply a half by to get rid of the fraction? Well, you multiply it by 2. If I multiply that entire equation by 2, I get what's shown right here. 2H2 plus 1O2 gives me 2H2O. Now, we could even represent that just by using a space-filling model. So that's what's shown right here. Now, what they're showing here with these gray spheres is that these are representing molecules of H2, right? I have 1, I have 2, and then I have a molecule of O2, right? I have 2 oxygens attached together like that, and when they combine, they form H2O, right? H2O. Let's make sure that this is balanced, and I'm sure that you can tell that it is, but let's go over it. I have 1, 2, 3, 4 hydrogens on the left. On the right, I have 1, 2, 3, 4. That works out. On the left, I have 1, 2 oxygens, and on the right, I have 1, 2 oxygens like that. So that is perfectly balanced out. Now, how would you describe this reaction to a friend or a colleague or a reader? There's a couple of ways. You could say 2 molecules, 2 hydrogen molecules plus 1 oxygen molecule gives you 2 water molecules. That perfectly works. You could also think about this in terms of moles, right? The numbers that are in front in the balanced equation. Here we have the number 2. Here we have no number. That implies the number 1, and here we have the number 2. We call these coefficients, okay? And you'll hear me call them stoichiometric coefficients. And what those mean, what they really mean is that if you have 2 moles of hydrogen, it reacts with 1 mole of oxygen, and you form 2 moles of water. Now, does this reaction obey the law of conservation of mass? Absolutely, it should. And if you tally up the mass of 2 moles of hydrogen, 2 times 2.02, you get a mass of 4.04. So that's the total mass of hydrogen in 2 moles of hydrogen. If you tally up the mass of 1 mole of oxygen, you get 32. Now you tally that all up and you get this number that I can barely read, okay, but it's 36.04 grams. Now look at water. The molar mass of water is 18.02, and we ended up with 2 moles of it. Look what we get. We get 36.04 grams of water. So the law of conservation of mass was obeyed, right? If we start out with this many grams, 36.04 grams of reactants, we should end up with 36.04 grams of product. Now, that's a lot of jibber jabbering for me on one slide, but if I had to boil it down, if I only had 60 seconds to explain the whole darn thing to you, I'd tell you that most of the time we're going to talk about these equations like this. We're going to think about the stoichiometric coefficients in terms of number of moles. You're going to see me do that over and over this evening. Give me a thumbs up if you follow me thus far. It's just kind of the introduction, the reactions. It's not supposed to be anything mind-boggling. Just good. Thank you, Sierra. Good, Chris. Excellent, Trevor. Whole gang. Perfect. Okay, Shay. All right, let's move on from there. Okay, so how to read chemical equations. This is just more rehashing of the same thing, but hey, repetition is a good thing when you're trying to learn. It says here, let's say we had 2 magnesiums. So 2 magnesiums plus plus 1 oxygen gives you 2 magnesium oxide, right? You should practice your nomenclature, magnesium oxide. Anyhow, there we go. Now, how could you read that? Now, you notice that I was careful. I didn't say anything. And there's actually, I just noticed there's a mistake in here. Let me point it out to you, in case you haven't noticed already. Right here, this should say moles. Anyhow, we'll figure that out in a second. But if I look at the first equation right here, it says, okay, I could read that and say 2 atoms of magnesium plus 1 molecule of oxygen. Now, why am I saying atoms and why am I mixing up molecules? Because magnesium, if I just read Mg, that's an atom, right? If I look at the periodic table, it lists all of the atoms. I see Mg, it's element number 12. On the periodic table, I don't see O2. I see O. Oxygen, if it's just O, that's an atom. But when you have O2, that's a molecule because you have 2 oxygen atoms combined, okay? So you got to be careful on your wording here. So 2 atoms of magnesium plus 1 molecule of oxygen makes 2 formula units of magnesium oxide. And you might get frustrated and say, well, why is this called a formula unit? Why? Is because this magnesium oxide is an ionic compound. Remember, I told you we don't talk about molecules of ionic compounds. We talk about formula units. Now, again, most of the time in this class, I'm going to read these equations just like it's shown here. 2 moles of magnesium, you add 1 mole of oxygen, and you make 2 moles of magnesium oxide. And then sometimes this evening, we're going to be looking at quantities of reagents. And so if you look up from the periodic table, if you figure out the mass of 2 moles of magnesium, it's going to equal 48.6 grams. If you add up the mass of 1 mole of oxygen, O2, it's going to give you 32 grams. And if you add up the mass of 2 moles of magnesium oxide, it should equal 80.6 grams. Now, here's a trap that students, not you guys, but other students fall into from time to time, is this right here. Every chemistry textbook on the planet Earth always has some iteration of this, where it tells the students, beware of this mistake. Do not try to do this. And students don't do it a lot, but sometimes people will just get it on an exam and they'll say, oh, well, this must mean 2 grams of this plus 1 gram of that gives me 2 grams. No. We cannot do that. We have to compare the number of moles, okay? So I'm not going to harp on that too much because I think I even showed you in another slide earlier on. Now, you saw me balance a chemical equation earlier on this evening. Now let's talk about some strategies that we would use for balancing chemical equations. It says here, number 1, you write the correct formulas, right? Okay, that's a good idea. For the reactants on the left, the correct formulas for the products on the right. Now, here's an example. It says ethane reacts with oxygen, form carbon dioxide and water. Now, there's something here which is ethane. I would not expect you to know what the molecular formula of ethane is, okay? That, I'll tell you right now, the formula of ethane is C2H6, okay? And I'll help you out. It's a gas. Now, the formula of oxygen, right? If it's combining with oxygen, it's not combining with a single atom of oxygen. It's combining with molecular oxygen, O2, right? And O2 is what we breathe in the air. There's what part of what's in the air is a gas. And then you should know how to write out the formulas for carbon dioxide and water. You should know that carbon dioxide is a gas, and you should know that water is a liquid, okay? So again, ethane on a tester exam, I wouldn't expect you to know that. I would give you that, but I would not give you oxygen, carbon dioxide, and water. By the way, whenever you have a compound that's made exclusively from carbon and hydrogen, like ethane, if you have any molecule that has the formula CXHN, we call those hydrocarbons. Hydrocarbons, and you've probably heard of them before because octane is a hydrocarbon. That's what you put in your gas tank. Propane, which is probably what you use in your barbecue grill, that's a hydrocarbon. Butane, that is found in a butane lighter or a butane curling iron or whatever, that's a hydrocarbon. So hydrocarbons always combine with oxygen to give you carbon dioxide and water. Now let's balance this baby out here. It says change the numbers in the front of the formulas, which those numbers are called the coefficients. We're going to change those around to make the number of atoms on each element on the same on both sides of the equation. Do not change the subscripts. Subscripts are these, okay? You never edit subscripts. Those you cannot change, okay? Those are no man's land, so we'll delete all that. Don't touch the subscripts, all right? What's next? Next, we have start by balancing those elements that appear in only one reactant and one product. Well, let me just show you what my strategy is here. Let me tell you, you guys like tricks? I know my students all like tricks. They're like, show me the easiest way to do this. Whenever you have a combustion reaction, so a hydrocarbon plus oxygen gives you carbon dioxide and water, I can tell you what the answer is right now. The answer is always this. You always save oxygen for the very last. Okay, it's the last thing that you look at to balance. Why? Because it's by itself, and you can literally put any number in front of that you want to balance the equation. Let me show you what I mean. Okay, we're going to start with carbon. If I look in my ethane molecule, I have 2 carbons. I only have 1 on the product side in my carbon dioxide. So I'm going to put a 2 there. Now my carbon is balanced. If I look in my ethane molecule, I have 6 hydrogens. On the product side, I only have 2 hydrogens, and that's in the water molecule. Now, what times 2 is going to give me 6? Who could tell me what times 2 gives me 6? I know you know the answer, but I just need to take a drink of water here. Yeah, thanks, you guys. The answer is 3. Absolutely. Okay, so we're going to put a 3 in front of, I'm going to grab my Apple Pencil here, a 3 in front of the water molecule like that. Now, the next step is going to be this. We're going to tally up all the oxygen atoms on this side. Who could tell me how many total oxygen atoms are on this side, on the product side? Not a trick question. Yes, thanks, Bruce. He's exactly right. There's 7, right? There's 7 total. There's 3 from the water molecules, and there's a total of 4 from carbon dioxide. So there's a total of 7. Now the question is this. What times 2 is going to give me 7? Who could tell me that? What should I put in front of my oxygen to balance it out? What times 2 will give me 7? 2 times what equals 7? Not a trick question. Trevor's got it, right? It's 3.5. Yeah, 3.5 times 2 gives you 7, right? If how 2 times 35 cents gives you 70 cents. I don't know. Anyhow, but so why don't I just put 7 over 2 here? Because 7 halves, right? 7 divided by 2 is 3.5. 3.5 times 2 gives you 7. Now my equation is perfectly balanced. Give me a thumbs up if you see where I'm going here, that I have a balanced equation. Cha? All right, thanks, Chris. Okay, perfect. So what I have to do now is I'm going to multiply this whole darn thing by 2 so that I get rid of the fraction. Now, I don't have any problems with fractions, but again, ACS doesn't seem to use them. So now we're going to have 2 molecules of ethane, which is a gas like that, plus 7 molecules of oxygen gives you 4 molecules of carbon dioxide, plus 6 molecules of water. Now I can guarantee you that this is a perfectly balanced equation with no fractions. Again, there's no big problem with fractions, just generally we don't leave them in. All right, let's take a look at an example. It says here, when aluminum metal is exposed to the air, a protective layer of aluminum oxide forms on its surface. This layer prevents further reaction between aluminum and oxygen, and it is the reason that aluminum beverage cans don't corrode. In the case of iron, the rust or iron 3 oxide that forms is too porous to protect the iron metal underneath. Anyhow, Write a balanced equation for the formation of aluminum oxide. Well, look, what's it giving us? It's telling us that the aluminum metal, so if it's aluminum metal, it must be aluminum that's a solid, is reacting with what? Oxygen from the air. Okay, I know that there's other gases in the air, but it's reacting with the oxygen is what it's telling us. So aluminum plus oxygen gas is giving us aluminum oxide. Now it's telling us that it forms on the surface. It's a protective layer, so it must be a solid. So we'll put Al2O3, and that's a solid. Now we have to balance this thing out. Well, let's do this kind of slowly here. Do you want me to give you a second to look at it? I'll give you a minute to see if you can balance it yourself instead of me just doing it for you. Let's give it the old college try. Does anybody have it figured out? Can anybody tell me what the coefficient they put in front of aluminum was? Somebody put 4, yeah. I don't think that's unreasonable. Okay, so that tells me that you're definitely on the right track. So Trevor, Tyler, Gabriel, they've all said 4 aluminum. So let's see. How did they get there? Well, let's do it slowly. Okay, I've got 1 aluminum here and I've got 2 aluminums in the product side. So that means I need to at least put a 2 here. Okay, I've got 2 oxygens here and I've got 3 over here. What times 2 is going to give me 3? Right, you could solve it like this. You could say 2 times x equals 3. X is equal to 3 divided by 2. Right, so if I put 3 over 2 here like this, that means I have 3 oxygens, 2 aluminums, and I have 3 oxygens and 2 aluminums over here like that. The reason that my students all said that they had a stoichiometric coefficient of 4 in front of the aluminum is because they took this entire equation and they multiplied it by 2 to get rid of the fraction, right? To get rid of the 3 over 2. And when you multiply that whole spinach by 2, you get 4 aluminums plus 3 oxygens produces 2 aluminum oxide, like that. Walla walla bing bang. Thanks, Gabriel. Wrote the whole darn thing out. Perfecto. All right, well, let's move on from there. And this is what I was telling you before. Okay, any chemistry textbook on the planet Earth always has some iteration somewhere in the pages of this exact figure that's shown right here. Okay, and all this figure is telling you is that you can't convert from mass of A to mass of B, okay, directly. Cannot be done. No, don't do it, okay? You always have to go from mass in grams to moles, then use a what? Balanced equation to get to moles of B, right? And then you can convert to mass of B, okay? So what does this hinge on, right? If we think about what this figure is showing here, all these things that I highlighted in yellow, this and this, these are both things that we looked at last class, okay? Things that we both looked at last class. This here, going from moles of A to moles of B, hinges on one thing, having a balanced equation. And that is why you've always got to start by writing a balanced equation. In fact, hear ye, and I'm recording this so we have a permanent record of it. From now on in this class, every reaction that you see from now until December, I always want you to ask yourself, is this reaction balanced? Sometimes I will give you balanced reactions. Sometimes I will not. It depends. Am I going to tell you every time? Heck no. Okay? This college, you have to look at it and say, is this equation balanced? So always be on the lookout for an unbalanced equation to brighten up your day. All right, let's see here. Hey, speaking of unbalanced equations, there's one right here, and this is a problem. It says the food we eat is degraded or broken down in our bodies to provide energy for growth and function. A general overall equation for this very complex process represents the degradation of glucose to carbon dioxide and water. So there's the equation shown down here. It is not a balanced equation. So we're going to have to figure that out. And then it says if you have 856 grams of glucose that's consumed by a person over a certain period, what's the mass of carbon dioxide that this person is going to make? Well, the first thing we need to do is balance this equation. So let's write it out. I'm going to write it out here a little bit bigger so I can see. So C6H12O6 plus oxygen. I'm not going to stress about my phases of matter right now. And there we go. So let's balance this baby out. Let me show you how I do this. Look, I have 6 carbons here, and I only have 1 in carbon dioxide. That means I need 6 here. I have 12 hydrogens here, and I have 2 here. What times 2 gives me 12? The answer is 6. Now I tally up all the oxygens on this side. I have a total of 12 plus 6, which equals 18. What times 2 gives me 18? And the answer is 9, like that. And so I balanced the equation. So here's my balanced equation for the combustion of glucose. Now I'm going to take that balanced equation and I'm going to solve this part of the question right here. If I start out with 856 grams of glucose, how many grams of carbon dioxide am I going to make? Well, let me start by copying all this spinach over here. So let me copy this guy. There we go. Copy. And then we'll move it over here. There we go. All right, so let's do some dimensional analysis. Now, I've gone ahead and I've looked up both the molar mass of glucose and the molar mass of carbon dioxide. So I'll help you out here. C6H12O6 is 180.2 grams per mole, and carbon dioxide is 44.01 grams per mole. Okay, so now I have those. All right, so here we go. Did I not consider the oxygens and glucose? Oh, I didn't balance my equation properly, did I? Let's go back, retract everything I said. So if I have 18, yeah, this would be a 6. There we go. This would be I made a mistake. Okay, he was going too fast. So look, on this side we still have 18 oxygens. Here we have 6. We need to have 18 oxygens over here. We subtract 6 oxygens. That means we got to have 12 right here. So 6 times 2 gives me 12. All right, does that help? After my faux pas, I was testing you, Gabriel. Better? Right. Copy. Here we go. Paste. There we go. Fixed it. Take this. We will banish it. Delete. All right. Well, with that in mind. All right. Good. Thank you. Good. I'll give that the old thumbs up. Good. Thanks for noticing that. Going a little too fast. Okay, so let's try some dimensional analysis. And we're going to start with the amount of glucose that we're given, which is 856 grams, right? That's shown right here. So let's start with that. We're going to start with, I'll write it out in black. We have 856 grams of glucose. I'm just going to put GLUC like that. And if we want to figure out the number of moles of glucose, we know that in 180.2 grams of glucose, we have 1 mole of glucose, like that. Now, if I was to stop right here, right, I would end up with the number of moles of glucose. Who can tell me where I should go or what I should do to figure out the number of moles of carbon dioxide? If I want to go from moles of this to moles of that, where am I going to go to get a conversion factor? Anyone? Where would I go to get a conversion factor? To convert the number of moles of glucose to the number of moles of carbon dioxide. Right, 1 mole of glucose to 6 moles of carbon dioxide, but where did you get that from? Where does that come from? Exactly, that comes from the balanced equation. Look, if we scroll back here, go back to this slide right here. If we want to compare moles of A to the moles of B, what do we have to use? We have to use the mole ratio from a balanced equation. And we have a beautiful balanced equation. And so we know that when we have 1 mole of glucose, right? So we have 1 mole of glucose. We don't have a coefficient there, but when we have 1 mole of glucose, we produce 6 moles of carbon dioxide, so 6 moles of CO2. So moles of glucose cancel out, and we know that in 1 mole of CO2, we have 44.01 grams of CO2. And so moles of CO2 cancel out like that. I'm left over with my mass of CO2. How many sig figs should there be in my final answer? Could anybody tell me? Thanks, Bruce. You're exactly right. There should be 3, right? Because I have 3 significant figures right here. There should be 3 significant figures in my final answer. And so I'm going to have to report it in scientific notation, which gives me 1.25 times 10 to the power of 3 grams, like that. Okay. Seems like things are pretty quiet here, but give me a thumbs up if you follow me on that question, because if so, that's a good thing. Cha, all right. Chris does. Okay. Well, if everybody's not entirely sure, or even if you're only partially sure, what do you say we try another one? Go into the free. Give it the go here. It says an alkali metal. All alkali metals react with water to produce hydrogen gas and the corresponding alkali metal hydroxide. Look, if you go down to alkali metals from lithium, if you throw lithium in water, you know, it'll do some fizzing and make some bubbles. And then if you throw sodium, usually it'll make some shrapnel and catch on fire. And then if you go to potassium, that will just poof, you know, ignite really quickly. I'm not sure about rubidium and cesium, but I know they're even more reactive than potassium, so I don't want to mess around with those. Anyhow, it says here that a typical reaction between lithium and water is shown right here. Beautiful reaction, right? Lithium and water gives you lithium hydroxide. And the hydrogen gas, that's what those bubbles are right there. Blah, 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 blah. All right, how many grams of lithium are needed to produce 9.89 grams of hydrogen? Well, we know that we want to make 9.89 grams of this, and we want to know how many grams of this do we need to do that, right? Somebody comes up to you and says, look, if you can just make me 9.89 grams of hydrogen gas, I'm going to write you a big check for $200,000. And you're like, well, how much lithium do I need to buy? You know? So you want to know the exact amount. The first thing that we're going to have to do, though, is balance this equation. So let's get the old pen out here. So we have lithium, solid lithium, plus water gives us lithium hydroxide plus hydrogen gas. Now, you might have noticed there's a really easy way to balance this equation, because if you look at it carefully, here I have 1 lithium, 1 lithium. Okay, I have 1 oxygen, 1 oxygen. Here I have 2 hydrogens, and here I have 1, 2, 3 hydrogens. All you have to do to balance this out is put 1/2, right? 1/2 in front of hydrogen like that, because 1/2 times 2 gives you 1. Now you've got 1, 2 hydrogens, and here you have 2. So that's an easy way to do it. But now, if we don't want to leave the fraction, we're going to have to multiply this whole thing by 2. And now we're going to write out our balanced equation, which would be 2 lithiums. Somebody's mic is unmuted. Plus 2 waters gives you 2 lithium hydroxides plus H2 gas. And the beautiful thing about balancing equations, I mean, there's a lot of beautiful things about balancing equations, but is what? You can always check your work. Okay, there's nothing stopping you from checking your work. Take a quick peek. 2 lithiums, 2 lithiums. 4 hydrogens, 1, 2, 3, 4 hydrogens, and 2 oxygens, 2 oxygens. Walla walla bing bang. Perfect. So let's delete all that spinach. Now let's get back to basics here and try the problem. Well, let's solve this using dimensional analysis. I have already gone ahead and looked up the masses of H2. So the mass of H2 is 2.02 grams per mole. And I've gone ahead and looked up the molar mass of lithium, which is 6.94 grams per mole. So now we have those under our hat. All right, well, let's start out here, and we're starting it with 9.89 grams of H2. That's what we want. We got to convert that into the number of moles of hydrogen before we can get the number of moles of lithium from our balanced equation. So we're going to divide that by the molar mass, which is 2.02 grams of H2 in 1 mole of H2. If I was to stop right here, which I'm not going to, I would end up with the moles of hydrogen, but I want the moles of lithium. And I know that for every 1 mole of hydrogen, I produce 2 moles of lithium. Let's write that in. 1 mole of hydrogen gives me 2 moles of lithium, like that. Looky, looky. Moles of H2 cancel out. Now they're asking me for the mass in grams of lithium. So I'm going to use the molar mass of lithium, which is 6.94 grams of lithium in 1 mole of lithium, like that. Look at this, moles of lithium cancel out. Is this a beautiful thing or what? You punch all that spinach into your calculator and you end up with, how many sig figs should I have, Bruce? You seem to know the last time. Or anybody. Chris, good, perfect. What did you put? Okay, good. Everybody put 3. Yes, I should have 3 sig figs. Why? Because I have 3 sig figs in this mass that was provided. So my final answer is going to be 68.0 grams of lithium. So all you got to do is go to the lithium store, buy 68 grams of lithium. You combine that with water, and you, my friend, will make 9.89 grams of hydrogen. You collect it. I don't know what you're going to do with it, but anyhow, you could. All right, let's look at one more, maybe 1 or 2 more concepts before we call it quits for the night, because we got to get over to the lab. If you are in group A, we have the lab, basic lab techniques tonight. Remember to bring your pre-lab completed so I can check it. Let's see here, limiting reagents. A limiting reagent is the reactant that's going to be used up first in the reaction. Okay, so if you have carbon monoxide plus hydrogen to produce this molecule here, CH3OH, that's methanol. It's the alcohol that you use as a fuel in fondue. Okay, so if you like to make fondue, yes, lab is at 7 p.m. Yes. So let's see here. If you look at this reaction here, you can see that you have the H2 here. So this is H2, and we have 1, 2, 3, 4, 5, 6 of those. So we have 6 molecules of H2, and then the CO2, or sorry, for CO rather, CO we have 1, 2, 3, 4 molecules. Well, if it takes 1 molecule of carbon monoxide and 2 molecules of hydrogen, right, you can see that I'm going to be limited by the amount of hydrogen that's in here. How do you know that? Because if I have 4 molecules of CO, right, and I know that for every 1 molecule, or for every 1 mole of CO, I produce 2 moles of H2 from my balanced equation. That would mean that I need 8 moles of H2. I don't have 8 moles. I only have 6 molecules, right? So 6 molecules is what I was saying. So that means that you're going to be limited by the amount of hydrogen, and that means that carbon monoxide is going to be in excess. If you look in the reactions then, you have some carbon monoxide left over. Look, a simpler way of thinking about this is, let's say you wanted to make, throw a party for your best friends, and what do you make when you invite your best friends over? Hot dogs, right? So let's say you had, these are, what's this going to be? Is this a bun? No. So if you make, let's say you have 3 hot dog buns, okay, 3 hot dog buns, but then you have, I don't know, 1, 2, 3, 4, 5 wieners, okay? So these are the hot dogs, okay? How many, I guess those are called wieners, aren't they? Anyhow, how many total hot dogs could you make, right? Well, if it takes 1 bun and 1 wiener to make a hot dog, you're limited, right? You could only make a total of 1, 2, 3 hot dogs. There we go. And you'd be left over. This looks more like hamburgers, don't they? Yeah. you'd be left over with 2 wieners, right? So that means that your buns are your limiting reagent. Does that make sense? Buns and wieners? I don't know. That's what came into my brain. Well, let's look at a problem. Let's see if it helps. Does anybody follow me on limiting reactant, the concept that I'm trying to explain here? Limiting reagent or limiting reactant, it's the same thing. Okay, good. Limiting reagent, sometimes I'll call it limiting reactant. It's the same thing. Okay, cool. All right. Well, let's try a problem here. It says that urea, first organic compound ever synthesized by a human being, by Friedrich Wöhler, a long time ago, was prepared by reacting ammonia with carbon dioxide. It's not a balanced equation, is it? We have 2 nitrogens, so we need a 2 here. 6 hydrogens, 6, 2 oxygens, 1, 2 oxygens. Okay, so it's balanced now. So that's how you prepare urea. So this is urea. This is ammonia. This is carbon dioxide. Anyhow, what's the reaction telling us? Or what's the question telling us, rather? It tells you that in one process, you're taking 637.2 grams. In one process, you're taking 637.2 grams of ammonia, and you're reacting it with 1,142 grams of carbon dioxide. And they're asking you, which of the two is the limiting reactant, and how much urea can you form, and how much of the excess reagent is going to be left over at the end of the reaction. So we're going to need some space to solve this problem. So let's move over here. Still don't think there's enough room on that slide. Anyhow, so let's work this out. Okay, what we're going to do first is we're going to write down the molar masses of ammonia and of carbon dioxide. And so the molar mass of ammonia, I'll write it up here, is 17.03 grams per mole. The molar mass of CO2, we had that earlier on this evening, it's 44.01 grams per mole. And the mass of urea, so the molar mass of urea, let's just write it like this. Is 60.06 grams per mole. So we're going to need all of these, and we're also going to need our balanced equation. So what we're going to do is we're going to do 2 sets of calculations here. We're going to start with our ammonia, and again, we have 637.2 grams of ammonia, and we have 1,142 grams of carbon dioxide. So let's start with our ammonia. We have 637.2 grams of ammonia, and we're going to imagine that we have all the carbon dioxide in the universe. We are not going to be limited by carbon dioxide. And let's see how much urea we would produce. Well, from my molar mass of ammonia, I know that in 17.01 grams of ammonia, I have 1 mole of ammonia, like that. Okay. And I know that from my balanced equation, when I use up 2 moles of ammonia, I produce 1 mole of urea. I'll just write urea like that. When I stop right here, that's going to tell me how many moles of urea I'm going to end up making. Now, let me get my calculator out here. And we have 637.2 divided by 17.01. divided by 2, and that gives me 18.7, so 18.7 moles of urea. Now we're going to do the exact same exercise, but for the carbon dioxide. We're going to start out with our 1,142 grams of carbon dioxide, and we're going to imagine that we have all the ammonia in the universe. We are not limited by the amount of ammonia, and we're going to figure out how many moles of urea we would end up with. So let's do just that. I know that I have 44.01 grams of carbon dioxide and 1 mole of carbon dioxide from my balanced equation. I know that 1 mole of CO2 produces 1 mole of urea. I'll stop right there. You can see the grams of CO2 cancel out, moles of CO2 cancels out, and if I take 1142 divide by 44.01, that gives me 25.9. So 25.9 moles of urea. My question to you is, which one of these is the limiting reactant? Is it ammonia or is it carbon dioxide? Which one's the limiting reactant? Yeah, it's ammonia. Why? Because it's produced in a lower amount. So there's makes less urea. Therefore, NH3 is limiting reactant, like that. So I've already solved the first part. Ammonia is my limiting reactant, and I'm going to end up forming 18.7 moles of urea. So that's part A. In part B, it says calculate the mass of urea formed. I know that I make 18.7 moles of urea, and I know that urea has 60.06 grams of urea in 1 mole of urea, like that, okay? Again, units cancel out like this. I take 18.7, I multiply it by 60.06, and I end up with 1,123. Now, technically, I should only report this, or no, technically, I can report this to 4 sig figs. In fact, I should have had 4 sig figs all along. Whoopsie doodle. I should have 4 sig figs here and 4 sig figs here, shouldn't I? Anyhow, I digress. Let's move on, and we'll just say that you end up with 1,123 grams like this. In fact, let me fix 637.2 divided by 2. So it's 18.7, 18.73 moles of urea, and 11.2 divided by 44.01 is 25.95. So let's fix that one too. 25.95 moles of urea. So it should be 18.73, like that. There we go. All right, good enough. All right, and then the last question asks us, how much excess reagent in grams is left at the end of the reaction? Well, if I'm consuming all of my ammonia, all I have to do is work out, well, how many moles of carbon dioxide would I use up, right? And I already know that I'm going to use up. Let me write it here. If I copy this over here, like this, I'm just trying to make it a little bit quicker for the sake of time. If I copy this over here, oh, I'm running out of space, aren't I? Well, let me just show you how to do it quickly. You would end up with like this, and this would tell you the number of moles of ammonia that you've used up, but you want to figure out the total number of moles of carbon dioxide that you've used up. So you end up with, no, I want to figure out the number of moles of carbon dioxide I used up, don't I? So, oops, there's not enough room on this slide. running out of room here.